So, for example, we talked about reactions where you have reactive hydrogens. We talked about they being quenched. Let's say we had a bromide and we had something like this. What would happen if you treat this with magnesium? If you treat that with magnesium, you would make magnesium bromide here, but that has another functional group within the molecule. It will react with itself, and so you cannot just quite isolate magnesium bromide. What would happen is this would react with either one molecule here, or it would react with other molecule of the same particular group. So at the end, what you would have is a messy reaction, because whenever you have more than one reactive functional groups, you cannot make it to react with one functional group. Even though you don't want it to react with this carbonyl, you cannot stop this from reacting with itself. These are kind of called detrimental reactions, right? And you cannot control them. You don't have control over the reactive functional groups. The same is true when you have bromide like this. Let's say you have OH. You have an alcohol functional group and you have a bromide. And I want to make a Grignard reaction out of these. So I treat this with magnesium and ether, and I wanted to try, and let's say I'm interested in making this one. Sorry, magnesium bromide. Okay. So I want to insert magnesium between bromine and this carbon, and I want to convert this into a Grignard reagent. But as soon as the Grignard reagent is formed, you have a protein group in here, protein alcohol. So this reacts with water. Remember, we don't want water to be around when you want to make the Grignard reaction, or any protein solvents for that matter. This has hydroxy group within the molecule, so you cannot make this magnesium bromide keeping this hydroxy at the other end of the molecule or anywhere in the molecule. If you have any reactive functional groups, you've got to think of something that's called protecting group strategy. So what I would do is, I would change the color of myself. What I would do is I take my bromide compound and alcohol that I have. Before I throw in the magnesium into this compound, I would first protect this hydroxy group so that it doesn't interfere with my reaction. So I would convert this into, let's say, methyl ether. I would just take sodium, some kind of base, and then methyl iodide, TMSCl, for example. So you take some base, like triethylamine is a base, and then you add trimethyl silyl chloride, some silicon chloride it is. So this would make TMS ether. So what we are trying to do here is we are converting the reactive functional group into an ether. TMS is a trimethyl silyl ether. That's the silicon chloride. So when you have O minus, let's say we converted this bromide into O minus, this O minus would attack silicon chloride bond, and as a result you can make trimethyl silyl ether. Once you have this trimethyl silyl ether, it doesn't have to be trimethyl silyl ether, it could be any ether for that matter. Just what you are trying to do here is you are taking the reactive functional group and you are converting that into an ether. So I can put an R group on this oxygen. So it's no longer protein. The hydrogen has been taken off. So now I can throw magnesium to this reaction. And then I can probably insert magnesium in here and I can convert that into magnesium bromide. And it doesn't react with itself now because this has been protected as ether and these ethers are chemically unreactive. So what are we doing here? We are protecting the interfering functional groups. You want to do the reaction here, but you have an interfering functional group here, so you need to protect that interfering functional group using some sort of protective group. So this is like a mask phosphate kind of mask. You are masking the reaction at the other end. You're done with the reaction, you can go back and peel off the mask. Do whatever you want to do with this ring out, then go back here and take this R group, you would convert that into oxygen. This strategy in synthesis is called protection and deprotection strategy. Okay, you are protecting this functional group because you don't want to lose that functional group. At the same time, you don't want it to interfere in your reactions, so you resort to something called protection. That's our unreactive. So as I said, ethers do not have much of chemistry to themselves. They are unreactive. The reason why they are used as solvents. But if you force, let's say this phenol has been now protected using ethyl group. So this is called phenyl ethyl ether, and your job is done. You want to unmask the hydro or this phenol. So what you do is you try to deprotect this. You try to cleave it off. So ethers can be cleaved using strong acid. If you have hydrogen bromide or HF, we can reflux them and they will undergo some reactions at this carbon-oxygen bond, and you can regain your alcohols and alkyl halides. This is the reverse way of making ethers. We talked about that. Williams and ether synthesis makes the ethers. Acid cleaves the ethers to get to the alcohol back. Okay? They're generally unreactive. You need strong acid. And this is like an SN2 reaction. If you have a bulky alkyl group on one side, a small alkyl group on the other side, your bromide would react onto this carbon, attacking that carbon. Carbon, hydrogen, right? So this bond is polarized towards oxygen because oxygen is more electronegative. You have delta negative here, delta positive here, and you have a nucleophile in the form of bromide because you have HBr. This bromide would attack this carbon. Why not this carbon? This carbon is more sterically hindered than this carbon, so this would rather prefer to go to this carbon, though this is also delta positive carbon. So less sterically hindered carbon would be attacked by bromide, and as a result, these electrons would be moved onto oxygen. So you would get CH3, CH4 minus, CH2, CH3 plus methyl bromide, because bromide attacks the methyl, right? So it's attacking here and it's forming the bond. So this carbon cannot have pi bonds, it's breaking a bond onto the oxygen, oxygen is getting negative charge, and bromine is now attached to the CH3. So you cleave the alcohol into an alkyl halide plus O minus. This O minus would become OH because we have H plus here. That would pick up the H plus and become an alcohol, right? What alcohol would that be? It would be a CH3, OH, CH2, CH3. This is kind of butanol, 2-butanol. This 2-butanol should have stayed as 2-butanol, but we are getting another bromide. Why is that? This we understood because the bromide is attacking this carbon, and this should have become an alcohol. An alcohol would have stayed like that. But remember, in the alcohol chapter, we learned that whenever an alcohol is treated with an acid halide, it can be converted to alkyl halide. So now you have to remember the alcohol reactions. This is an alcohol. It doesn't play just a spectator role. It would undergo protonation because you have HBr. So this OH gets protonated, this bromide gets knocked out, and the bromide comes back and attacks this carbon. As a result, you get the bromide. So this is an alcohol reaction. This now alcohol is not an ether. We are talking about ether reactions. Ethers get cleaved with the acid, but this acid can also convert alcohols into alkyl halides. So instead of getting one alcohol or one alkyl bromide, we get two bromides here, right? The other alcohol also is becoming bromide. But in this case, if you remember, we cleaved this ether using HBr. In one case, we had an alcohol. In the other case, we had a bromide. The bromide is attacking this carbon in SN2 fashion, and these electrons are moved onto the oxygen, and as a result, you get an alcohol. But this alcohol stays as an alcohol because this is an sp2 carbon. There cannot be a substitution as an sp2 carbon. Right? So this is an sp3 carbon in the previous next slide. So whenever you have a aliphatic alcohol, simple alcohol, not enols or phenols, alcohols cannot stay as an alcohol when you have strong hydrohalide. They get converted to alkyl halide. That's what we learned in alcohol chapter, right? Any questions about it? So you have to learn how to tackle these problems by looking at this, not only one product, but the other side also. This is the one which we talked about. That's the mechanism. First step is the protonation. That was missing in the previous slide. This oxygen gets protonated so that this bond gets further polarized. So because of this oxonium ion, that's why we need a strong acid, because this is a weak base. Has a pair of electrons, but is not ready to donate that pair of electrons unless the acid is strong. So this hydrogen is very polarized, H plus almost, Br minus. So you get protonation of this oxygen, that in turn polarizes these two carbons. So the bromide now can attack this carbon, and as a result you get methyl bromide. And this becomes an alcohol because it's already protonated. So either you can protonate at the end of the reaction or in the beginning itself. These are acid catalyzed reactions, so we'll have it protonate in the first step itself. You get the bromomethane, and this alcohol further undergoes reaction with HBr, and that becomes another type. So instead of ending up with one alcohol and one bromide, when you use the ethers, you normally end up with two bromides, especially in the presence of nucleophilic HBr. If I had H2SO4, probably I could stop. Just leave the stage one, I can probably make one alcohol out of it. But sulfate is not a nucleophile, so normally we use hydrofluoric acid like HBr, HCl, HI. Okay. Let's take this case. We have a cyclic ether here, and we want to cleave that ether. This acid cleavage of ethers, and we are using HI. So the first step is the protonation. Oxygen gets protonated, and as a result, you have only one pair of oxygen electrons on the oxygen. It had two pairs, but it donated one pair to the H, and I got removed, and as a result, you get I minus. That I minus comes back and attacks one of these carbons, either this carbon or this carbon. Both the carbons are symmetrical, so it doesn't matter where it attacks because this is positive charge. But this cannot attack here because of this polarization. And this carbon is also delta positive. So as a result, this attacks here. And that is broken. And one end you get iodide because iodide is attacking. The other end you have OH. But this OH doesn't just keep quiet, it reacts with HI further. And that's the reason why it gets converted into two ions. This iodide comes back. This iodide is leaving from here. That I minus comes back and attacks here. And all these leaves. Okay? So, one step at a time. Just do the protonation first, and then you attack the iodide on this carbon, and then push this bond onto the oxygen. As a result, you know that one side is attached to iodide. The other side is still attached to alcohol. But the alcohol now becomes the alcohol that we learned in chapter 17, and it's converted to iodide. So you got to learn how to do these cleavage reactions when you have hydrohalic acids. Remember that it's a strong acid and you need high temperatures, then only you can open the ethers. Otherwise, ethers are very unreactive. That's the mechanism I talked about. So I'm going to skip that slide. So first step is protonation. That's something which is important to remember. Second step is a SN2 reaction because this is a good leaving group now. If it is cyclic, it's attached, though it's a leaving group, but there is another reaction. That's one of the reactions of ethers. In the presence of strong acids, ethers can be free. The other reaction is specifically for phenyl allyl ethers. This is phenyl. This is phenol. And you are also elevating it. This is allyl bromide. Whenever you have phenyl allyl ether, this is for phenyl allyl because this is allylic. This is the allyl bromide, right? And you get phenyl allyl ethers can undergo rearrangement when you keep up to 200 or so. These electrons undergo a cyclic movement. It's called pericyclic reactions. We'll talk about this when we get to chapter 30 in case we can make it chapter 30. So what happens is these electrons go in a cyclic motion. This pair of electrons would move there, that pair of electrons would move there, and this pair would move here. So there will be a CC bond formation between these two carbons. So this outside group gets transferred from oxygen to carbon. So this is called Clayton rearrangement, process called sigmatropic rearrangement. Clayton is a scientist who came up with it. The process is called sigmatropic rearrangement. all the electrons are moving in a cyclic form, so it's also called a pericyclic reaction. Whenever we have movement of electrons in a cyclic form, that's called pericyclic reaction. These are the reactions that we know are sort of pericyclic reaction, right? If you have the diene and the dienophile, you could make these sort of reaction to work, and you could make this thing, right? In chapter 14 or so, you learned in 21. It's the same thing. Here the electrons move in a cyclic transition states, or in no transition states, that sometimes they will just go undergo cyclic movement of this electron here, these electrons go here, and these electrons go here, and as a result, we form the ring. So that's similar to Binswanger reaction. The electrons are moving in a cyclic transformation or a cyclic reaction. It's specific only for these ethers. It has to have a panel ring or a vinyl group here. There should be 6 atoms, and the double bond should be 3 position. Let's say start with oxygen and go this direction. That's 3. If you start from that direction, and that's 3. So 6 atoms are connected with each other, and the pi bonds are at the terminals. When you have this kind of a system, these electrons can undergo cyclic motion, and as a result, they reorganize themselves, and you form a new type of bonds, carbon-carbon bonds, out of the expense of carbon-oxygen bond. So you form the carbon-oxygen bond to make the ether, heat it, you convert this carbon-oxygen bond to carbon-carbon bond. That's why it's called rearrangement. You don't have any other reagents. Right? You don't have electroparts, you don't have nucleoparts, you don't have any carbon acids or bases. Perturbant reactions sometimes. There's no intermediate, there's no carbocation or carbanion involved. But anyhow, at your stage, this is all you need to learn. But advanced stages, we teach a lot more reactions like this. These reactions were invented by Claisen, by scientist named Claisen, so that's the reason why it's called Claisen rearrangement. Any questions about Claisen rearrangement? Any questions about previous features? It also gets cleaved. The carbon-oxygen bond is cleaved, but it doesn't take off. It gets connected on the other end. As a result, it's called rearrangement rather than a cleavage. All these slides are up there, and I hope you don't have to done everything. Just pay attention and see if you can understand the concept, and then go back and make your own notes. Okay, so now we'll move to some other class of compounds which are called epoxides. Epoxides are also ethers, but these are cyclic ethers. Because of the ring strain, this is a 3-member ring, and because of the strain, these ethers have much more chemistry to themselves rather than if they were to be open. Let's say I had an ether like this. This is dimethyl ether. This is not as reactive as this ether. I cannot do many reactions at this carbon or this carbon, but I can do quite a few reactions here because this ring wants to open up itself. It is very sterically and electronically destabilized. There's a lot of energy built into this thing. It's like taking a small string and trying to connect on the other side. So you have a lot of potential energy in the string. It wants to open up, right? The same is true here. You have a lot of torsional strains and bond strains, angle strains involved. As a result, these ethers have some chemistry to them compared to the linear ethers or open ethers. Okay? So these are called epoxides. And you have 3 members. They are called algeranes. And epoxide is also a common term that we use. And this particular epoxide is called ethylene oxide because this comes from ethylene. If you take ethylene and oxidize, you can make ethylene oxide. It's like manganese. If you oxidize manganese, you call that as manganese dioxide, right? Or manganese oxide. The same is true here. You're taking an alkene and you're oxidizing it, so you call this as an ethylene oxide. So these are normally prepared from alkenes with an oxygen source, right? In this case, it's prepared from ethylene, but it doesn't have to be ethylene. I could have something like protein, and still I could oxidize it, and then I would have another here, right? So these are all called epoxides generally. Epoxide is anything that has a 3-member ring. It doesn't have to be just this epoxide. It could have an alkyl group or an aromatic group. Still we call this as an epoxide. Right? Why are the epoxides highly reactive compared to linear ethers, non-cyclic ethers? Because look at the energy levels of these two ethers. Normally, at room temperature, if you measure the inbuilt potential energy into these molecules, these are at higher energy. Already they are at higher energy, so the activation energy is very less to open. So this is the product. This is the level of energy level of the product. So if you have to go from this reactant to this product, you got to cross this energy barrier, which is very high. Whereas in the case of epoxides, you already have the reactants at a higher energy level, so you are going down. This is thermodynamically favored than this uphill process. It does have a little bit of uphill process here, but this activation energy can be easily supplied to temperature or a little bit of heat. You have to heat it to 150 or 200, right? So you learn all this thermodynamics and kinetics in chapter 5, right? In Chem 251. So that's still applicable here. So what are the reactions that we can do? We'll look into that. First, we'll quickly review what we learned before Chem 251. Whenever you have an alkene, you can do the epoxidation using MCPBA. This is MCPBA because metachloro, that's the meta position, metachloro. If this were to be the only functional group, we would call that as benzoic acid. But whenever you have two oxygens attached to a carboxylic group, that's called per acid. Per acid. That means we have one more oxygen or peroxy acid. That's acid, right? Just we have a carbonyl and one oxygen attached to hydrogen, but if there are two oxygens, so this oxygen is in turn attached to other oxygen, so it's called per acid. This is acetic acid, only one carbon or two carbons here, and this has two oxygens, so it's called per acetic acid. It doesn't matter whether it's per benzoic acid or per acetic acid, it just needs this peroxy acid. And if you have metachloroperbenzoic acid, it's much more easy to purify because this benzoic acid is solid or we can wash it off by carbonate, and you transfer this oxygen to this alkene, and as a result, alkene is epoxidized. Okay, you're not transferring this oxygen, you're transferring this per oxygen, right? This bond is much weaker than this bond. So what's the mechanism? The mechanism is sort of butterfly mechanism. That's all this. It's also given by a scientist called Krigi. It's also called Krigi mechanism. Don't have to remember the name anyhow. So you don't. So electrons are moved in a cyclic form. So the first, this alkene is acting as a nucleophile, so it's donating its electrons to this oxygen. This oxygen is delta positive maybe because of this carbonyl effect, carbonyl and oxygen. So this oxygen is much more labile than this oxygen. So this is donating the electrons to this oxygen, but this oxygen already has two pairs of electrons, so it cannot keep another pair of electrons. So this bond breaks, and as a result, this bond breaks. This carbonyl picks up this hydrogen, and there are a couple of electrons here. Those electrons come back to this carbon. It's like bromonium ion reaction. Bromination you did in Chem 252, sorry, Chem 251. Whenever you have an alkene, you have a bromide, you give electrons to bromine, and as a result, you get a bromonium ion, right? First it becomes Br, and on the other side you have a positive charge, but bromine has lots of these electrons, so it gives one pair of electrons back to this carbon, as a result to make a bromonium ion. The same is true here, but just that there's a couple of more atoms. Trans alkene, you get trans epoxide. Thereby we know that everything is happening in a concerted in a cyclic fashion. Can you see this slide? If not, I can explain to you. So that's how we made the epoxides. Epoxides can be made either by using peroxide, like hydrogen peroxide can be used. What is hydrogen peroxide? We have one more oxygen, water form. H2O is water, H2O2 is peroxide. So this peroxide bond is important for epoxidation. Alkenes can be epoxidized using either peroxide or paracids. Some of the paracids. See, once we know how to make epoxide, we look into the chemistry of epoxide. And let's say when you have an epoxide like this, either your nucleophile attacks here or here, it doesn't matter because these two are symmetrical, one another. There is no difference. You get the same product, whether this attacks here or here. But when you have an epoxide like this, where one end of the epoxide is different than the other end, then you have a nucleophile. And the nucleophile has two options. Either it can attack at this carbon or it can attack at that carbon. This carbon is highly sterically hindered. This is not so sterically hindered. But depending upon the nucleophile, either you can open this ring from this end or you can open from that end. Depending upon the attack of the nucleophile, you get two different compounds. So you got to know where to open this epoxide from, where to attach the nucleophile. And there are two ways to open this epoxide. We are opening the ring, but there are two ways to do that. One, where we take the help of acid. So this is called acid-mediated epoxide ring opening. So we know that there is some acid always on this arrow. If you see some acid here, the first step is the protonation of this oxygen. Let's say we had, redraw this epoxide for the benefit of those data features. You can see that. Anything that you have an acid is a source of proton. So either you use H2SO4 or you just use H plus, it doesn't matter to me. When you write the mechanisms, you can just use H plus. And one of these pairs is related to this H plus, and as a result, we call this as a protonation. And in this protonation process, we are activating these two carbons for nucleophilic attack. Because this is picking up the proton, as a result, now this is almost ready to break the bonds. This puts the electron density further from these carbons towards those positions. And as a result, these carbons pick a little bit of positive charge and they become delta positive. I'm talking about these carbons. Okay? So this delta positive is much higher here than this delta positive. Why? You remember again from 251 that the primary cation is less stable than a secondary cation, which is less stable than a tertiary cation, right? Stability-wise, a tertiary cation is much more stable than a secondary carbocation than a primary carbocation. That means there is more positive charge here than here than here. It's very difficult to form a carbocation and a positive carbon, and a primary carbon. If you transfer the cation here, this is like a secondary carbon, this is the primary carbon, right? So the where do you think the positive charge would be more? The positive charge would be more stabilized than this carbon, and because of this methyl group, also this overlap of the orbitals in this direction. So the nucleophile acid medium is attacking at the more hindered carbon. That's the take-home message in this slide. Whenever you have acid medium, you are activating your electrophile. This is your electrophile. Epoxides are activated, and the nucleophile attacks at more hindered carbon, more sterically crowded carbon, more substituted carbon. That's something you got to understand. When you have two options, the nucleophile could have attacked at this carbon or it could attack here. It prefers this carbon because there is more positive charge here than here. This is not activated. This is a neutral nucleophile. What is activated nucleophile? If I had sodium methoxide, activated nucleophile that I have it's charged. O is charged, right? Oxygen is charged as minus. So this is a stronger nucleophile than just methanol. Why does methanol act as a nucleophile? Methanol has two pairs of electrons on oxygen, and it can act as a nucleophile when you have an electrophile, strong electrophile. If you just mix the oxide and methanol, probably it would take forever to react, forever to open this thing because this is not activated. But if you add a little bit of acid, you can protonate your electrophile, and in that case, even the less reactive nucleophile. these are called neutral nucleophiles. Neutral nucleophiles can be made to react with electrophiles that is called. But when you have this electrophile, you don't need that. It is a strong nucleophile. And as a result, you can just mix that with epoxide and you can get the reaction to work. Okay, so there are two ways to open the epoxides: acid mediated opening, base mediated opening. In acid mediated reaction, the nucleophiles attack highly substituted carbon. Yeah. This is for H2S. That's the first way, protonation. Right? We'll look into the mechanism. It opens up because this is attacking here. So these electrons are moved here. So this positive charge becomes neutral. So that becomes a OH. Right? And now whatever this CH3OH, that becomes CH3, OCH3. When you do a protonation, at the end you need to do a deprotonation. Protonations and deprotonations are very common. I think we have a slide for the mechanism. We'll look at it. We'll come back to the mechanism. Just give me 1 minute. This is base mediated ring opening where you don't have an acid here on the reaction acid. So there's no acid, there's only base. Sodium methoxide, for example. Right? Or it could be potassium methoxide. It doesn't matter what the counter ion. What matters is here the nucleophile is activated. We are not activating the epoxide. In acid medium, we had activated the epoxide by using protons as a protonation step, right? But this step is not possible here. We don't have protons available in basic medium. We only have anions available. But these anions are activated nucleophiles, so you don't need to activate the epoxide. And where do they attack? They attack at the less hindered carbon, because this is like an SN2 reaction. In this case, it's like an SN1 reaction. You have a carbocation, a little bit of delta positive charge and all those charges that we talked about. Here there is no charge on the epoxide, so to speak. So this is an SN2 reaction. SN2 reaction prefers less hindered carbon. Right? SN1 reaction. More happy at the first. Any questions about it? So if you use the same invariably you make alcohol when you open epoxides because oxygen is opening one end and that is negatively charged. But the question is what alcohol do we make? That depends on what medium do you have. If you have an acid medium, you make primary alcohols. If you have a basic medium, you open from this end, so the oxygen gets attached to this carbon, so you normally make secondary alcohol. Right? You have to remember to analyze this reaction by looking at the reactions that are given to you. So this is an epoxide, this is a basic medium because you are seeing hydroxide, right? You're not seeing any acid here. So this is attacking from a less hindered side. This alcohol is made on the back. You could have opened from here if you use acid. Okay? So this is again basic medium. You have methanol, that doesn't matter, it's not an acid. This is the actual nucleophile here. And that is attacking from the left hindered side. This is also the intermediate. First it attacks here, this becomes O minus, and you have sodium plus, that becomes an oxide. But when you have protic solvent or water around when after the reaction, that's called what cup. So in basic, there is no protonation to activate your electrophile. There is only activation of the nucleophile. These nucleophiles are much stronger than what we use in acid medium. Okay? So they attend the SN2 reaction. We open the left hindered side. Okay, when you have symmetrical, it doesn't matter. This is symmetrical epoxide. Whether you attack from here or from here, doesn't matter. So, but what I want to draw in analogy here is these epoxides are similar to bromonium. The first step when you do the bromination is the bromonium ion formation. We already talked about the bromonium ion formation mechanism. And this bromonium ion is not stable, so other bromide comes around and then that can attack either here and can attack from there, and again depending upon substitution pattern, you get the products. But in here it is alkene, and this is symmetrical reagent. So end up with this carbon oxidation, this carbon bromine. But in here the case is different. Nucleophile is different. As a result, it is alcohol. Other species connecting here. In this case, we have a water as a nucleophile. So it appears as though we have two alcohols. But these alcohols, look at this stereochemistry. One is pointing beta bond that is coming towards you. This hydroxy is going away from you. So you are getting trans diox by opening the epoxide. That's what is taken here. When you have bromonium ions, we made dibromides by brominating the alkene. But if you remember the stereochemistry, these bromides were going in anti-addition. We talked about syn addition and anti-addition in alkenes, right? The same is true here. Epoxides can open only from the opposite face of it. If the oxygen is facing towards you, the nucleophile cannot come from the other side. It comes from the back side. As a result, the two groups are going in opposite directions. You get trans diols in case of water as a nucleophile, but even in the other cases, when you have other nucleophiles, let's say we have HCl, it could be HBr or HI or HCl. So the H is used for protonation because it's the acid medium. So both in epoxide, it is activated now. It's a positive charge because it's attached to hydrogen, and this carbon or this carbon can react with beta bond, and the incoming nucleophile will come from the other side. Let's say we had HCl, and this is symmetrical, so I can attach from any side, and this would be, but the product would be something like this. This alcohol will be coming from the top face, but the chloride is from the other side. So not only writing the product is important, but also showing the stereochemistry is important. Got it? If you don't have stereochemistry, you don't have to worry. But if this stereochemistry, the oxide is shown as a chemically pure compound, then you have to show the stereochemistry in the product as well. Okay? Any questions about epoxide opening? We'll go back to some of the mechanisms as time permits. This is halohydrin formation, right? In the halohydrin formation, you have fluoronium ion, and the fluoronium ion is opened with hydroxide. As a result, you make halohydrin, but look at the stereochemistry of the halohydrin. They are in the opposite direction, right? This is from beta bond, this is alpha bond, this is going away from you, this is coming towards you. Or if you have a plane out like this, one is going upwards and one is going downwards. But if you have halohydrin, this is another way of making it. Halohydrin is base, here, and then minus intramolecular nucleophile substitution. This chloride gets kicked out. As a result of the absorb here, this gets epoxidized. So the alkenes can be epoxidized using chlorine and water, halogen and water, bleach, for example. Bleach is nothing but HCl or H2O, right? It's oxygen. So something like that can be invoked, or you can go stepwise and do the chlorination and then open the hydroxide and water, and then you need halohydrin. Halohydrins are disposed for the Centuri reaction. So the Centuri reaction happens when you do the sodium hydroxide and base, intramolecular nucleophile substitution that makes epoxide. And now if I have a nucleophile, I can open up this. So alkenes are really useful because of epoxide. You can do some chemistry, some different chemistry, and you can functionalize. Okay. So if you have a nucleophile such as the R minus, you can open epoxide that we talked about in Grignard reactions, and it's a symmetrical epoxide, so I can attack from any side. And one of these carbon-carbon bond forms, and then as a result, this carbon-oxygen bond breaks, and you get an alcohol in the tummy. Okay? So if I have an alkene like this, I can make this compound going through oxidation, and once the epoxide is formed, I can use now nucleophile to open that, depending upon the group. I can choose my non-reagent, and I can attack on either side with the vertical epoxide. Doesn't matter which we have there. And you get notice that the incoming nucleophile is coming from the opposite face of this epoxide. If the epoxide is on the top face of the cytopentane, the nucleophile is coming from the bottom face. We have to show that these are the tags. Okay? And this is a summary of the discussions we had. If you have an unsymmetrical or asymmetrical epoxide, the substitution pattern is different than these two compounds. Different substituents, different size of the substituent, different number of substituents. This doesn't have any metal, it has two metals. So these two carbons are differently poised for ring opening reaction. So when you have acid, you open from the highly hindered carbon, highly substituted carbon. That's an SN1 type of reaction. When you have bases, you open it from the less hindered side and you get highly hindered tertiary alcohol, secondary alcohol, resultant of base-mediated opening of the epoxide, acid-mediated opening reactions normally give you practical. Okay? And you can make disubstitute, 1,2 disubstituted compound. Not only make alcohol, but also you can bring in a nucleophile. Depending upon your nucleophile, you can form carbon nitrogen bonds, carbon sulfur bonds, carbon carbon bonds. So it's widely employed synthesis. Some of the reactions you can see here. Thiol can be used as a nucleophile. And this is a base-mediated reaction. So this attacks from less hindered side. As a result, you make one side thiol because you have thiophilic thiol nucleophile, and the other side you have oxygen, so you can make thioalcohol. You can make alcohol, which is water. If you can use acetylide as a nucleophile, this is anion, carbanion. So carbanion, and this is the base. This attacks from the less hindered side. As a result, you make alcohols. If you have an amine, you can open from less hindered side. Sorry, amines are basic, so again you open from less hindered side. You make amino alcohols. If you have nitriles, you can use it 3 minus. So it looks like N minus, but it's attached from the carbon because it's a right resonance structure. Attached from the carbon, and then you make cyanoalcohol. If you have lithium aluminum hydride, you can add hydride, and that hydride also comes from less hindered side. So this is basic again. So anytime you have a charged nucleophile, nucleophiles can be two types: neutral nucleophile or charged nucleophile. Charged nucleophiles normally open from the less hindered side. Neutral nucleophiles, such as water, methanol, ethanol, are charged because they have electrons. They can act as nucleophilic centers on these atoms. So they open from the highly hindered side. Okay? Charged nucleophiles. The same nucleophiles can be charged, like OH minus, CH3O minus, and they can get open. Okay? So depending upon what I need, what I have, either I can activate my electrophile or I can activate my nucleophile. In this case, it has to be acid-mediated nucleophile because this nucleophile is not charged. So you have to recognize the pattern, how to write. The two groups are going in opposite direction. The nucleophile is coming from one side, the other group is going in the opposite direction, and there are two carbons away from one another. You are not attacking on the same carbon. You are not getting the substitution of the alcoholic carbon. You always make 1,2 substituted products, 1,2 disubstituted products rather than 1,1 disubstituted or 2 disubstituted. That's something you have to remember. And you're also responsible to know the mechanisms, and you are responsible to use them in synthesis. Okay? So go through some of these slides where I've shown some synthetic applications. Okay? And if you have any questions, we can talk about it. With that, we'll close this chapter and move to the next chapter.